is our tank. So so what so we have a water. We have water just filling up the tank, right? So we have water filling up the tank, and through which there is a pipe. There's a pipe in the bottom, which is filling up the tank. Now we need to keep a reference level. That is, we need to tell the controller which level till which level we want the water to be filled in the tank. That is our input. Okay, that is our reference level. Okay, reference level. So this is something which we give input to the controller, right? You can say not to the controller. We compare the reference and the feedback and give the error to the controller, right? Okay. So now what is the now input? I'll just write the input. That is m dot mass flow rate. What is mass flow rate? Dm by dt, right? That means rate of change of mass flow, kilogram per second. How much kilogram of water is input to the tank per second, right? So that is our m dot mass flow rate. So what is my output? The output is nothing but the volume of water in the tank. It is 100%. That means full. It is full. Tank is full. Right? 0% is empty, and this is maybe 80%. So that is my reference shilling. I need the volume to be 80%. Okay. So you can see here the input is the mass flow rate m dot kilogram per water second, but output is the volume. So we are trying to control the volume. So how we are trying to control the volume? By giving some water, so water kilogram, some mass of water into the tank. Now who decides this, how much water has to be put in the tank? Now this has to be decided by the controller we are going to design, right? So this output has to be done by the controller. For example, how are you controlling the mass flow rate? How the controller is controlling the mass flow rate? Maybe it is directly controlling the motor. If we need to increase the mass flow rate, it increase the power of the motor, something like that, or the voltage, which is directly proportional to the uh, the torque of the motor or the rotation speed of the motor, something like that. So controller is going to control some parameter by which my m dot or my mass flow rate is going to change, right? My mass flow rate is going to change means my volume of water is going to increase, right? So till what point? Till my reference point has been reached, right? When my reference point is reached, then my error is becoming zero. Why my error is become zero? Because error is nothing but reference error is nothing but reference level minus present volume. Right now, what is the volume of the water existing? So here we can see the error is positive, right? This is error which is positive because the current volume of water in the tank is very less and reference is higher. Okay, so error is positive here. Error is positive. So how we reduce the error? We can increase the volume of water. How we increase the volume of water? By increasing the m dot. We can improve the m dot or make the water on or the tank is on, right? So in a conventional, in our home, we don't need say complicated or sophisticated controller. We just need to have a on off switch. You should understand this very carefully. In our home application where we are filling water in the tank, we don't care whether the error is reduced in less time or it's taking long time. We are more concerned about saving water. We don't need water to flow or get waste. Electricity is wasted, water is wasted, or temperature, motor get burned or something. But in this when you're designing controller, we have more concerned about the error. I need to reduce my error as fast as possible, right? That is most important. So my controller should be intelligent enough to understand the level of the error, and accordingly it should act or give in or improve the mass flow rate, m dot something, m dot, right? So what is the advantage? So my error is reduced. So my, we can say, system response, how the system is responding to the error. Yeah, this is very interesting. This is very important if you are talking about real-time systems. For example, we are talking about a car which is trying to be controlled by reducing the error. What is error here? Maybe the lane, the difference between the lane 1 and lane 2. If you are going to lane 2, it is dangerous, so reduce the error. This should be very fast. So here the example of controller is more valid and more important because it is real time. Okay, so this is the yesterday's example. Now let me draw the model. So let this be the model. So we have a controller. This is controller. Okay, we need a controller. Now what is the input to the controller? Input to the controller is error, right? How much error is current error? right? Based on the error, the controller will give some output. Here, for example, we can take E is the input to the controller. We can say C as controller output. C, right? And let me be C. C is the controller output. Okay. Now this controller output has to be going to the tank. This is our water tank where we already given a reference level. This is the reference level. So where we give the reference level? The reference level is input to the system. This is the reference level R. I call R. Right? This is plus. Now how the error is calculated? By the feedback. Now the volume of the water tank is the output. Volume is the output. Volume of the water tank output, and this is going to the as negative, right? So this is gives me the error. That means reference minus output. This is output. So we can say, how can you write? Let be V, volume V, right? So V is going to be feedback to the, there's an adder in front of the controller. So this R minus V here. Here the error is going to be R minus V. Okay. Now based on this error, my controller should be act very intelligently so that it can control the C. C is actually nothing but the mass flow rate, m dot. Right? C is nothing but mass flow rate of change of mass of water in the tank or the going inside the tank through the pipe. There's a pipe here. M dot is the rate of change of or rate of mass transfer into the tank. That is M dot. Okay. So this we have discussed yesterday. So this is the controller. So controller input is the error, and based on error, there is some process done by the controller. We are not discussed till now that point, and then I giving output C. Okay. Now based on the water level, current water level, and the reference level, uh, there's an error generated and it is again going back to the controller. Okay. So based on this error, controller has to do something. So yesterday we discussed one type of controller, that is proportional controller, right? So we try to model the controller, like we try to model, say we try to derive, there's a mathematical equation, but we want a algebraic equation. There was a calculus, there's a d by dt. So we know m dot is nothing but d by dt of m, right? Rate of change. So this m is volume into density, right? So d by dt of volume into density. So we try to model like that, but density is constant, d by dt into volume. So the volume is what? Now we try to mathematically model the volume, right? Then we try to integrate both sides to like to remove the d by dt or calculus term, differential term. So we integrated both sides and we finally came across one mathematical equation. So this is kind of modeling. The relation between input and output algebraically is much simpler. Right? So that mathematical modeling we had just discussed. Now, yesterday we discussed proportional controller. So what about the proportional? What's the meaning of proportional controller? Proportional controller. Proportional controller is more simpler controller. I think yesterday we discussed. Where proportional controller is the controller where my output of the, let ut ut let ut be the output of my controller. Ut is directly proportional. So in this example we are taking c. Let ct be the, so usual standard textbooks give u as output of controller. So what is the meaning of, there's a controller whose output is u ut. This is input to the plant, right? So you should know the big picture. You should know the big picture. What is the big picture? We discuss the plan. What is the plan here? The water level. The water level. Water tank is the tank. This is the reference level, right? So this is the plant. So I'm giving some input to the plant, that is m dot, controlling the water level of the tank. So this is done by the controller. This is the controller. Okay. Controller is controlling the mass flow rate into the tank. Now what is input to the controller? Error. Okay. I think this much is clear. So here I'm assuming the output of my controller is ut. Laplace transform is us, but with some time it is ut. Error is et with respect to time. Okay. Error is et and output of the controller is ut. Right? So we are more concerned about the design of the controller. So we can see in proportional controller, we can see that ut, the controller output should be directly proportional to the error signal. This is proportional controller, right? So we can put a constant. That means the controller output should be equal to a constant k into et, right? This constant k I'll write as k with p. Substitute T, that is proportional gain of the proportional controller. K into, so this is the time domain equation of the output of a proportional controller. Okay, so this is we have discussed yesterday. Here this Kp is the constant. If I increase the Kp, you have seen that yesterday our response is going to increase, right? We have seen, right, yesterday we have seen, right, the input output Kara in one example. If this is the Kp, if I increase the Kp, what will happen? The curve will be shifting, the slope will be increasing. Now the sensitivity is much higher. Sensitivity is much higher, right? So initially this was my sensitivity, and right now input output relation is this curve. Right now in second thing my output is much higher. You can see much higher. These two things you can compare, right? The same input variation, my output is much higher in second case. So that means my Kp is higher, right? The system response has been much faster. Else, if Kp is less, my system, although it is directly proportional to the error, but it takes long time to overcome the error. That means it cannot be used for high speed applications because it takes long time, right? Okay, so Kp. Now, if we apply a Laplace transform onto this equation, ut, what will happen? Okay, if I apply a Laplace transform, we can see this will become something like this. I'm writing like this. If I Laplace transform, this okay, ut becomes us equal to kp into es. That's it. Es, right? So this is the transfer. Sorry, Laplace transform. Now, how to get the transfer function? Output by input. What is output? Output of your controller is us. So us by, we can say us by es. So us divided by es. Output by input of the controller will get kp. So this is the transfer function. Okay, so in a proportional controller the transfer function is nothing but kp, a constant kp. Okay, so this tank I can draw this tank, proportional control tank, like this. Very simple. Just this is my plant, this is my water tank, which is considered as a plant. Now this is the controller is nothing but a kp, a controller with a gain kp, something like, you can write this gain. This is my error, this is my output of a controller is going to the plant, right? Now this again, there's a feedback, like we know it's a feedback, and this is minus, and this is plus, and this is in my reference level r. Okay, so what is this r? R is a reference to which my plant level, reference level of the plant, right? And my output is nothing but the volume, how much volume is filled in the tank. So whenever you think of a plan, you just take an example, any simple example. That means that then you'll be able to relate with these parameters much more. If everything is theoretical, it's very difficult to. So that tank example is very good example, right? So output is, you're trying to increase the volume and you're comparing the existing volume with the reference volume, then errors generated, then it is increasing. The more kp means more responsive, more sensitive uh, your motor or your controller is towards the error. And right, okay, so kp. Now let's see, so how you design a controller in electronics. Since this is, you can see a simple gain, you're designing a system with a simple gain, so you can easily use an op amp to have give a gain, right? So this design is simple. You have an error, this is a voltage error. We can see this error, some voltage R. We are given R voltage as input, and the output volume VV. The feedback volume is getting, there's another voltage, and I'm getting a voltage error VE. So I need to give a gain to this voltage error, so that it'll giving a high output, high voltage output. So it is going to the motor or something, this plant. So how to give a gain? Simple gain. We can design a op amp circuit. So how it works? So you can see, you know how to design a simple op amp. So whatever the gain we have, what here the gain is kp. So say for example, um, so let me put this is minus plus. So how to say this is r. Let this is r. So what will be the rf? Let this is equal to kp times r, right? So if I give an input here, input here, I'll get a output here. Okay, so this is just a simple electronics controller. Controller can be designed in many different ways. The hydraulic controller, pneumatic controller, mechanical controller. So this is an electronic controller. How you design a gain? Very simple. Okay, so what is the gain in this setup? You can see how what is the gain here? V output by V input. V output by V input. So here you can say this is Kp into R divided by R. But there's a problem here. What is the problem? Can anyone tell me? What is the problem here? There's one problem. We want a gain, Kp. We are trying to design a gain, right, with the feedback resistance Kp into R. That means our R cancel. Now our gain is Kp. But there's a problem here in the circuit. It's not what we expect. Yes? What's the problem? Is everyone in the class, or are you busy somewhere else? Or you can type in the chat also. If there's a problem, you can type also. Okay, sorry, maybe I am muted or something. Okay, no answer. You can see that this is a gain of a inverting op amp, inverting amplifier. It is there's a negative, right? There's a negative which we don't want in our control system. So the gain actually is negative, and this is not what we want. Our gain in a proportional control should be Kp, not minus Kp. So what we will do? Yes. Yeah. You need to use another inverting op amp. Yeah, very simple. So we need to keep another inverting op amp. That is very simple. Yeah, this is what we do usually. We have a already op amp minus plus and a gain of how much? Gain Kp times R. If this is R, okay, this is grounded. Now we need to keep another unity gain op amp or unity gain op amp. You can just keep this R and this also as R, right? So this is V output. Now we can see what is the gain. Now this is V input. Now we know this V output by V input is multiplication of these two gains. What are the multiplication of these two gains? Kp into R divided by R is the first gain. Second gain is minus, right hand. Second gain is minus R divided by R. So we can see all these common R's are common. So this is cut, this is cut. We'll get minus Kp of Kp. We'll get positive Kp. Okay. So this is simple circuit for proportional gain. Okay. So okay. So how you design the control system after getting proportional controller? Just instead of controller, we just give the gain Kp. Now we have planned. So this is UT. You can say UT, output of the controller. This is error of the error coming from the difference of the reference and the planned output. This is planned. Okay. Now this is taken as a feedback. X minus and plus, and this is reference R. Okay. This is your proportional controller. Now we have seen the defect of proportional controller. The proportional controller, although it is working directly proportional, output is directly proportional to the error, but still in order to reach some level, for example, this level I need to reach, it takes long time. You can see this, so much time I'm ready. How much time here is required? You can see this much time is required to reach the reduce the error. If we increase the k value, still I can improve it, but maybe I can increase the k value. This is k equal to 10. Now if I k equal to 100, maybe like this, k equal to 100. Still, this much time is still there, still required to minimize my error. So I go on increasing my gain. That means there is some problem. Then we'll see what if I go on increasing to a proportional value to very high value. So that time there is a problem. There can be some instability. You can see, imagine if your reference is constantly changing. Imagine your reference is constantly changing. Then if the k value is very high, what will happen? You can see your output will have to be going like something like this. It's very dangerous. Okay, so there are a lot of subtle things. So let's improve. So in order to reduce all those problems, we need to improve the controller a bit intelligently. So we again uh, propose, like, why can't we use having a controller which works on the error, based on the residual error it should act, right? Based on the residual error it should act. That means if there is huge error, instead of difference in error, you should check the area of error, how much area. That means integration. That means we are going to design a integral control. So integral control. Okay, so in order to improve the proportional controller, we are going to propose integral control. So what is here the feature of integral controller? In the integral controller, we know the output of the controller should be directly proportional to the integral of the input. That is much better. Just instead of getting a proportional to the error, we also need to have a controller which works on the integral of the error. That is area of the error curve. For example, the controller output should be acting on the area of the error. Area of the error. Okay. Okay. So what will be its equation? This is proportionality. If I change the proportionality equal to constant, I call this constant ki, integral constant, into error term et. Let me take the Laplace transform. So this is us equal to integral. So this is dt, integral dt. So integral dt. So if I take the Laplace transform, integral, this becomes es divided by s, right? So what about the transfer function? This implies transfer function is nothing but uh, output of the controller divided by error of the controller in Laplace transform. That is nothing but ki integral divided by s, right? So this is the Laplace. This is the transfer function of a integral controller. That is ki by s. Okay, so it's act on the area of the error curve. If there is area is huge, will have proportionally this output will be increasing intelligently, rather than directly checking the difference of error and reference. That is different directly magnitude of error. That means difference of reference and the present output. We are directly output is directly affected by the error curve. Integration. There's nothing but integration. Integration nothing but area, finding area of a curve from time 0 to time t1, whatever. Okay, so this is the integral controller. So we know there is a integration here. So you can see that the controller should be designed such a way that I need a constant divided by s. This is my controller here. Now what is the input? Error is the input. What is the output? U is the output, and this is going to the plant, right? Again, the feedback and compared with the reference value, plus and minus, right? My error is going. So this is the integral controller. So there are some subtle topics which we'll discuss. The integral control gives a bit of instability to the system, and how it is giving instability we'll discuss later. But it has some advantages also. It can reduce steady state error very fast, right? So this is some advantages of. So how it is reducing the instability, sorry, how it reducing steady state error? Because it is improving the type of system. We'll discuss what is the type of system. There is type number of system, right? We'll discuss with respect to algebraic. We'll discuss when we discuss the Laplace transform and advanced concepts. Okay, so let's right now understand integral control, its own advantages and disadvantages. It reduces steady state error. but stability reduces. Okay, so there is a problem. Okay, so let's see how it is implemented. If implementation of the integral controller. So we know this is the integration. So there is always a capacitor, right? So we know this is op amp here, minus, plus, sorry, ground. Now I need a resistance and a feedback path. I'll keep a capacitance. Okay, you can see this is C. For example, if this is C, if this is R1. Now input is given to the op amp here, right? So again here also there is a you can see this is, if you put Laplace equation, you can see the gain of this system. This gain of this system is equal to RF by R1. RF is the integration, capacitor is the, so you can see if you um, you know 1 by Cs is the numerator, 1 by Cs is the gain of the feedback path, divided by R1, right? This is nothing but R1 Cs. So this is the, so here this is a negative term, definitely this is a negative term, right? Because it is a inverting amplifier. So in order to avoid that inverting negative, what I'll do, I'll connect one more op amp, unity gain op amp, minus, plus, same feedback resistance, R, R, right? So what happened? Now this minus change. No, this minus, need not worry about this minus because I have one more amplifier, right? So what is the gain? So we got the gain GS is nothing but 1 by R1 CS, right? So this is the gain of a integral controller. So we have designed a circuit for integral controller. I can give the input, which is nothing but the error, and the output will be the integral. Output will be the uh, C or US, which is going to input to the plant, is directly proportional to the integral of the input error. Here it is VI error. Okay, so you should know the transfer function, that is 1 by R1 CS. If this is the R1, if this is C, and this is RR, whatever. Okay, so you should know what is the proportional controller, what is the uh, um, integral controller. Now we know that the two disadvantages of the integral controller. One is stability reduces. So we have to propose another kind of controller which improve the stability, right? But it also have some of kind of the disadvantages. So that kind of controller we call derivative controller. Now here the in uh, derivative controller, what is the specialty? Our controller output will be proportional to the derivative of the input error. Okay, so that's it. This is the third type of standard controller we have. So here ut is proportional to the rate of change of error, et. Okay, so ut we can say is a constant, k derivative, kd into d by dt of et, right? Now if you take a Laplace transform on both sides, you can say us equal to derivative constant into s into es, right? So we can say derive the transfer function from this us output by input is error, is nothing but kd into s. Okay, so this is my transfer function of a derivative controller. The only thing is your s is in multiplication with the constant kd called um, uh, derivative constant kd. Okay, so this about the derivative controller. Now the derivative controller will improve the stability, but at the cost of steady state error. Steady state error will be increasing. So you should understand the output of the plant, output of the controller right now is dependent upon the slope or the derivative of the error. If error is changing at a greater rate, if error is changing, tan theta is very high. At this point, my error is going to be very high. If it is going to be zero or a slope, that means there is no change. If the error is not at all changing, that means my derivative controller output will be zero, right? So you should try to visualize its working. For example, this is based on time. So my error is, the error is going on constant rate. There's no change in error. Let me draw the reference value. This is the reference value. Reference. And this is the current. This is the current output. Current volume of the tank is this. So here there is no change in the error. Error is constant. So the my derivative control doesn't work at all. It maintains the output. So the error is maintained because there is no change in error. Right? So, but if the volume was changing based on the changing in the my the control acts on the rate of change of error. That means is find the slope. How much is the error is varying? Based on this slope, I'll generate a error signal, and my control output will be directly proportional to this slope signal. So this is called a derivative controller, right? So based on the slope of the error signal, I'm generating a function. So you can see that with only derivative control will not help in any way. Without only derivative control, you can see if the error is zero, it will maintain the error. There's no change in the error, so there is output will be zero or something. Okay, so only derivative control it doesn't work. It suits my purpose. So I should always use a proportional controller with a derivative controller at least. That is called PD, proportional derivative controller. At least why? Because only derivative control it only acts on the change of the error. Right? So if error is not changing, it is constant, but derivative controller will not do anything. So the error will be the same. Error will be constant. So there is no changing error. So okay. So I always should use a proportional controller along with the derivative controller. Okay. So it will be something like this proportional controller along with the derivative controller. Say we have a plant. It can be tank or water thermal system or temperature control system, whatever. You have output. Now this is your controller. So here if I'm using PD, proportional derivative control, I need KP, constant of proportional plus derivative on KD plus S, right? So this is my controller. So the acting on the error. So error is produced from the comparing the reference value and the present output value, plus and minus. Okay, so this is my proportional derivative controller. Okay, so this I can also write this in textbooks. You can see this is written as KP is taken out. So 1 plus KD by KP into S, which is again can be simplified by KP into 1 plus say constant T or something. Yeah, this one thing. How this came S is here. Sorry, S is here. S is here. Okay, so 1 plus TS, something like this. You can see in this textbook. So where T is equal to KD by KP, constant. Ratio of the constant of derivative constant to the proportional constant. Okay, so this can be written in different ways. Okay. Now, the proportional derivative control has a lot of problems because although stability is better, but steady state error is high. So we often use PID controller. So PID controller is nothing but we have the proportional controller plus integral controller Ki divided by S. This is the integral controller and a derivative controller Kd into S. So this is the PID controller. It has a lot of advantages because it also acts on the rate of change of error, that is diffusion controller, or it also acts on the residual error, that is accumulation of the error, that is the area under curve integration of the error by the proportional controller, and the output of the controller is going to the plant. Okay, again the feedback compared with the reference, and error is generated, error is going to the controller, and controller is giving output U. Okay, this is output O. Okay, so this is P proportional integral derivative controller, PID controller. Now we should know how to simulate this in a MATLAB. For example, maybe in next class, maybe we can discuss how we can simulate a PID controller. You should go to the Simulink model in a MATLAB. You have just type Simulink in the command window. You can see something will be opening. Some window, Simulink window will be opening. Maybe I can show right now. Maybe I have to connect again. So I will just tell you how to see and what to check, how to control a plant. So when you go to Simulink, lot of models will be opening, lot of models will be opening, continuous blocks, right? All this. So you can take an example. You can take simple transfer function, any transfer function. So there's a one transfer function. For example, you can put any value like this: s square plus 4s plus 4, something like this. This is a plant. So this is transfer function block in the Simulink model. Transfer function block. If you double click on the transfer function block, there is an algebraic expression you can write. If you write 1 4 4, it automatically gives the transfer function like this. If you put 1 and 4, it will make a transfer function s plus 4. So what is this? This is the coefficient of the s term, the constant term. This is the coefficient of s square term, coefficient of s term. This is a constant term. So as you can put whatever value. For example, if you put something like the 1, 2, 3, 4. Now the transfer function model is nothing but s cube, s cube plus 2s plus, sorry, 2s square plus 3s plus 4, right? So based on your number you're writing inside the transfer function block in the Simulink, your transfer function is generated. Okay. Now, for example, you have made a transfer function like this: 1 divided by s square plus 4s plus 4. This is your plan model, right? So this is your transfer function plan. No, this is output. This is output of your plant. This is input of your plant. Now you want the plant to follow some output, right? You give a reference. You want your plant to work based on a reference value. In the tank example, we are giving the reference value, how much water volume should be filled, how much volume the water should be leveled in the tank. So likewise, here also we can give some input there. So I give a reference value. So this reference, for example, in control system in the MATLAB Simulink, you should give some signal, a reference signal. So I am giving a step signal, right? So what is the meaning of step signal? Step signal. This is my signal which my plan should follow. Getting? That means my plan should follow my this reference value. For example, this magnitude is 1, the unit step signal. I want my plan to follow this signal. So that is a reference signal. Now what will happen? Now I need an adder block. This is plus, so minus. So this feedback again I have to give to the um, give to the input, so that now the controller. Now I need to keep a controller. Now in the transfer, in the Simulink model, you have different controller: proportional controller, derivative controller, PID controller, integral controller. So all those controllers are there. So for example, you're putting a proportional controller. Let me put a proportional controller. So you need to place a block like this. It's a proportion, or you can keep a PID controller and you can keep other constants as 0, right? You know, the PID controller has the constants, all these constants like this. What are the constants? Proportional constant plus integral constant and differential constants, right? If we keep this these values 0, this ki and k is 0, then it is a PID controller. The block will be PID, but the constant is proportional constant. So kp will be a proportional controller. Now my output should follow the reference. Reference is this unit step. You can say unit step. Now my output of the plan should also be a unit step. If it is not unit step, the feedback will give the value back to the input, and the error will be going to the controller, and the proportional controller should generate a output, that is u. Here I can say is ut or something. The input is, say for example, x. Let it be x, not u. So the controller output is u, and this u should be capable enough so that the planned output is like the step signal, right? So you can say this is a second order plan, second degree planned. So we can see, if you see the output now in the MATLAB, there is a output scope. There's a symbol like this, scope. Okay, so what you will do, you try to see the connect the output to the scope of the scope. Now also parallel to the output, you also want to see the output with respect to the input. So you also try to keep the reference signal also into the scope. The two signals are given to the scope in MATLAB so that you can compare the change of output, etc. Right? So what we have done, we just made a transfer function model in the MATLAB Simulink or any model, or for analytic purpose, we just make a model. So the equation is 1 plus 1 divided by s square plus 4s plus 4 transfer function, right? Now this is our plan. Now it has to be controlled by controller, right? Now the controller is here is a proportional controller. How we take the proportional controller? You can take a PID controller and make other constant as zeros. Then it is a proportional controller, and we have to give a value for the proportional constant kp, right? Now input to the controller is the error. Error is the output value compared with the reference value. Reference value we are giving a step signal x, something like this. Okay, so this is compared with the output, and now the proportional controller should act in such a way that the planned input should give a planned input such that the planned output is matching your reference. So you can see now, if we double click this scope, what we'll see, because we are comparing both input and output, we can see the reference signal. This is the time. My reference signal is already shown in the scope. You can see there is signal something like this, like this. There is signal something like this. This is my reference signal. So magnitude is there. Okay, and now how my plan output will be working based on the proportional control. You can see the plan output going something like this. If it is zero, it was perfect. So when it is this point, then my proportional control is going to act. Now this is going to match the match the output, right? So this is proportional controller KP. You can see it is going linearly only. You can see it's taking a long time. Okay, this is my proportional controller. Now if I improve it, if I add values for integral and differential controllers, constants kd and ka. So if I, the controller initially I have used kp only. If I use ki and kd also, so what change will happen? So what I'm doing here, I already have value for kp. Now I'm giving value for ki and kd also. Depends on the values. You can see the output is now different. Now you can see from the output is something like this. It is something better. You can see why it is improved, because I'm using a different integral and differential constant also. So my controller is not proportional. It's a PID controller. Now again, if I change the values of Ki and Kd and maybe Kp also, I can see different output. For example, maybe some output will be like this. It is much better. But still there is error. But ideally, it may not be the something output will be like this. Something like this should be something like. So we have to manage, we have to understand what value should I give of this kp ki and kd, so that my planned output is going to follow my reference input, right? So here the reference input, I already told you, reference input is what the input you give into the system input. This is the reference. This is, you want the plan to follow this input, right? So that is called reference input. Now the different output values like 1, 2, 3, 4 different are different controller output, right? If my planned output, when I'm using different types of controller, proportional controller, derivative controller, proportional derivative controller, PID controller, proportional integral derivative controller, PID controller, and different values of KP, K, and KD within PID controller, you give different outputs. So you don't know which constant has to be kept for KP, Ki, and KD, which value. So that is called tuning. This process is called tuning. Finding optimal value for this constant is called tuning. Tuning. What is tuning? Tuning of a PID controller or tuning of a controller is selecting the optimum values for the proportional controller, integral controller, and derivative controller, so that my plant the planned output immediately follows, or with less error or with great stability, right? It follows my reference input, right? So how to tune and how, what are the factors? It depends. That depends on application. What kind of application you're working? If you're working in a motor which is doing robotic surgery, you cannot you cannot have any steady state error. You cannot expect any steady state error. You should not have any delay also, right? It should be very highly, perfectly, heavy sensitivity and high responsive motor. That kind of, so the plan which we had just drawn represents a motor. It can represent, say, generator. It can represent a gyroscope, accelerometer. It can represent a factory also, complicated area. It can represent automobile. It can represent sensor. It can also represent, say, circuit. So you can represent anything. So the reference value which you give it to the uh, reference value which you give to the controller is the value what we expect, right? And we already discussed um, yesterday in the tank example, the output of the controller may not be having same physical relationship with the output of the plant. Output of the controller was the controlling of mass flow, that is mass of the water in unit time flowing into the tank. If it is positive, then means water level is increasing. If it is negative, means water has been drained out of the tank. So that is the controlling, which is what the controller is controlling. Okay, so this much I think for today. So if you have any doubt, I'll be happy to try to answer it. So tuning will discuss more deeper. So this is like application things. So in all the MATLAB, you can see there are tuning. So you can tune all automatically tune. You can keep the output as per your requirement. So MATLAB automatically gives you the constant parameters KP, K, and KD as per your best choice of your output. Whether you want one, you want to go for first wave, second wave, third wave, fourth wave. So depends upon that you can decide what. So MATLAB will immediately give you the lot of constants for KP, K, and KD. So it's up to your application. First of all, how much responsive you want, how much error you can keep, how much sensitivity you want, etc. So this is all about the different types of controller: integral controller, proportional controller, derivative controller. So you can also see the implementation of the derivative controller also. The only change and derivative controller you can see will be something like this. Now, PAM, you need to have a capacitor in the input definitely. So this is a derivative controller. Maybe you can need a resistance parallel to the capacitor also. Right. So you can keep like this, minus plus, this is grounded. Now need to avoid this negative, avoid this negative, avoid the negative in the gain. So I gain put once again, right? So this is R, this is R. So this is somewhat we can say derivative controller. Okay, so I think I don't need this R. If I keep a R, it becomes a PD, proportional derivative controller. Now this is a derivative controller, right? The capacitor is input. This is V input. This is V output, right? If I need to make a proportional derivative controller, it will be I need to keep a resistance in parallel to this capacitor. For example, R, or I can say this is R1, this is R2, something like that. So now if you calculate the transfer function, please try to calculate the transfer function of the circuit. You will get this is nothing but output divided by input, something like this. So what will come? It will be coming around something like this. R1 C1 S plus 1 R2 divided by 1. Try this. Are you able to get this transfer function from the circuit? Please try it. Okay, GS. There are two op amps. Here the gain is 1. Here gain is 1 in the second op amp. So maintaining the sign, to maintain the sign, like avoid the negative. Here now we know the gain of this op amp setup is negative, so gain of here is a negative, so negative, negative, positive. So this become positive. And the parameters also you can check. There's the capacitance, parallel the resistance R1, feedback resistance R2, and two resistance R and R. If you check the transfer function, please check the transfer function. Are you able to derive this thing? R1 C1 S plus 1 into R2 by R1. Please check this. Check out this. Okay. So if you have any doubt, please let me know. I'll try. Else you can put your roll number.